All right.
Got it?
So
Okay.
yesterday,
That's what it is.
So,
you start, every time we start, you start it out with,
all right.
okay. And you start here, and you like rub your eyes, look on the videos. Every single time it starts, it's,
All right.
okay. And I went through it, I tried to get a Snapchat story of it, but I couldn't get it. It's just, okay. Okay. It's every single one. I was dying last night watching it. Literally spent 10
he's like, good luck.
you were roasting me the day I wasn't here. You're like,
Really?
yeah, he's screwed.
yeah, hashtag unscrewed.
Yeah, that is it.
That was it.
But I still have to show you because it's funny.
Okay, you ready?
Okay.
All right.
Okay.
Okay.
All right.
All right.
Okay.
So, last question on that net forces assignment was true or false, if an object is going to get off the ground, the net force has to be greater than the opposing force. So look at it this way. Let's say that you're down taking weights class, right? And you want to lift 100 pounds. Okay? How much, if you just exert 99 pounds of upward force, what's going to happen?
Nothing.
Nothing. Now, imagine that you have this thing sitting on a set of scales, okay? And the scales are reading 100 pounds. If you exert an upward force of 99 pounds, what's the scale going to read? 1 pound, because everything still has to balance out. It's not accelerating. If you exert 101 pounds, will it accelerate?
Yes.
Yes. So the upward force that you have to apply just has to be greater than the downward force keeping it here. All you have to have is a positive net force to get something up in the air. The net force doesn't have to be greater than the opposing force. If that was the case, if that was true, then 101 pounds wouldn't lift this. You'd have to exert like 201 pounds of upward force to lift a 100-pound weight, because then that would get you a net force of 100 pounds, and then you could lift it. Okay? So you just have to have a positive net force. Okay? So your applied force just has to be greater than your opposing force. That's it. Okay? That's the only thing that has to happen.
I have a really good excuse for being late, though. You're going to love it.
I have no doubt. You curled your hair?
Yeah.
That was it.
That wasn't why I was late.
Oh, I thought that was the story.
They brought a toad into the office that got ran over.
A what?
A toad.
Just let it.
To the vet office. And they wanted us to, like, save it. Well, not me, because I don't have a license to do that, but they wanted...
It's a toad. I
Yes.
really don't think you have a special disposal license.
I thought it was really cool.
Okay, so did you save it?
No, it died.
All right.
It died. No, it died. Yeah, it died.
All right.
Okay.
Just run over.
Now, let's talk about the questions on the limb lab. Okay? And so, one of the things I talked about yesterday was the fact that the moon has no atmosphere. And this is one of the questions in terms of how this thing is going to move. So, to simulate this, we're not going to the moon, but this is the best I can do. So, what I've got here, okay, is a tube that's got like a silver slug and a feather, okay? So if I turn this thing upside down, the nickel falls very, very quickly, right? And the feather just kind of goes on its way down because of the fact that there's a large amount of air resistance. Now, hold back. So if I do the magic of a vacuum and basically turn this thing into space,
If you put sand in there, we die.
now, when I flip it over, they both basically fall at the exact same rate. The feather kind of gets hung up because of static electricity, but they basically both fall at the exact same rate. So when you look at this idealized situation that we always use of -9.8 meters per second squared, that is a very idealized situation. Because if there's any resistance at all, so like if I put air back into this thing, hold on, this one might get a little loud. I'll take this one off. So then when I put air back in and do it, that feather falls a lot slower again. So one of those questions on the lab was that in terms of the horizontal motion, is the calculation is going to be the same on Earth as it is on the Moon. When I was writing that, I don't want you to get hung up and go, oh, on the Earth there's some air resistance, okay? There is going to be a little bit of air resistance, I'll give you that, but that's what I was going for, is that you realize when you're talking about a horizontal motion, that there aren't any opposing forces acting horizontally. Vertically there is, but there aren't any horizontal forces that are opposing that motion. So when you look at that question on that back side, it's like, hey, is there any need to take gravity into effect when you're doing the horizontal calculations? Every one of these problems needs to start with this idea that force net equals FAP plus phi. This needs to be your first initial idea on every one of these problems. So if you're talking about that vertical motion, here's my question. If you shut off the engine vertically, are you always going to accelerate? Cubby, if I shut off that main engine vertically, will I always accelerate?
No.
Really?
Actually, yeah, you will.
If I shut off that main engine vertically, will I accelerate?
Yeah.
Yes. Why?
Because gravity will pull you down.
That's right. Vertically, this never goes to zero. You always have a gravitational force acting vertically. Now, when you talk about the horizontal motion, so if I want this thing to go in this direction, I'm going to fire this engine. So horizontally, especially on the Moon, is there an opposing force? No. Now, don't confuse inertia as a force. Listen to me. Inertia is not a force. Inertia is nothing but a tendency of an object to resist a change in its velocity. Inertia is not a force. If inertia was a force, we'd measure it in newtons, and it's not. Okay? So inertia is just a tendency to maintain whatever state of motion it has. So here's the dichotomy between, on this situation, what's happening vertically and what's happening horizontally. Vertically, this is never zero. You always have an external vertical force. You can have an applied force, okay, that can balance this out. You have an applied force that can be greater than this. But this opposing force never, ever, ever goes to zero. So that means even if you shut off the engine, you're always going to have a net force. I can make the net force go to zero, but my applied force would have to balance out that gravitational force. Now, horizontally, there is no external force that acts horizontally. Okay, it's not there. So the only time I have a net force horizontally is when what happens? When you have, what? No, making this difficult.
An applied force.
An applied force created by? The two engines on the side of the ship, right? You got to fire a rocket. Either that or you have, like, you know, Martian squirrels that will push the ship around while you're trying to land, which is just awkward because they tend to go on strike and they're unreliable. So, and there really aren't Martian squirrels. Don't, there aren't? Yeah. Okay. So, here's the deal. So, you can only create motion horizontally when you fire the engines. But here's the deal. Once you fire the engines and get it moving, you can shut off the engines and it will coast because there aren't any opposing forces. So here's the dichotomy. you shut the engine off vertically, you drop like a stone. Horizontally, the only time you accelerate is when you fire the engines. Okay? So that's one of the key things that you have to understand. Because inertia acts the same. Inertia vertically is the same as the inertia horizontally. It is like, oh, inertia is stronger vertically because of gravity. No. This thing doesn't want to change its direction in any way. It doesn't want to go up. It doesn't want to move down. It doesn't want to move horizontally. So if you're changing that velocity, there has to be an external force acting on it. Okay? So here's the drill. I'm going to go through. You're going to bring up that paper. I'm going to look over both sides of it. Once I sign off on it, then you can get the laptops and start doing the program. Now, let me talk about what's going to happen when we get to the program. So, the program you're looking for is a program called Interactive Physics 2000. You're going to have to go to, like, I think you have to, like, open or search all programs to find it, like it's in that icon in the bottom left corner. So, open up the Interactive Physics 2000. Now, this program that I have stored is in the L drive. So if you go to open, and then if you go to that L drive on the server, within that there's one called Burkamp Learner Program. Find that. This is what you're looking for. This is what you should see when this thing opens. Now, because this program was reinstalled on these laptops, when you open up the program, it might ask you, it's a weird question, it'll say, like, what is the last word on page 5-3? I've got the operator's manuals. So if you get that question, you got to find the operator's manual, open up to that page, find the last word on that page, and type it in. They do that so in case you have a bootleg copy of this thing without the operator's manual, you can't run the program. Okay, so it's just like a safety check that they put in there. Sometimes it does, sometimes it doesn't, but if it does, just don't flip out. So, you're here, come up here, clear this, click on that gray area, move the box, hit run. So, you're going to go up, we'll go down, go back up, go over here, and
slow down.
You're too fast.
I'm getting some.
Up.
struck it!
Oh, yeah.
Okay.
Wow, he's so easy.
This is my first rodeo. Okay, so here's what you're going to do once I clear this off. You get the program, you're going to try and land it. What you need, let me see, Hunter, God forbid you have your
I'll just pay attention, you know.
Yeah, okay, whatever. All right, so over here on page 2, or page 3, however you want to think about it. What you're going to have is a set of data. So what we're going to do in this section is that we're going to verify that the program is actually working, okay? Which is what any good engineer does. You never trust the computer program. So what you need to do is that you're going to pick 2 different points in the flight. Okay, this is like when it landed. Okay, I'll use this one. So you're going to come in here and you're going to record the acceleration in the vertical direction. So you're going to go AY, negative 0.27 meters per second squared. Then the velocity in the Y, negative 0.95. Then the value of the main thruster, 7,000 newtons. Now, is the value of my main thruster FAP, FOP, or FNET? FAP. Okay? So, look at this. This is my applied force. Upward force is 7,000 newtons. I have a negative acceleration. So, is my applied force bigger or smaller than the weight of the ship? I got an applied force of 7,000. I have a negative acceleration. So which one's bigger? My force going up or my force going down?
Yeah.
Up, down.
It's going down, so.
Yeah. No, it doesn't have anything to do with motion. Doesn't have anything to do with the direction. Because look, all this goes back to this idea that force net equals FAP plus phi. Now, here's the deal. Net force always equals mass times acceleration, right? So if I've got a negative acceleration, guess what? That means I have to have a negative net force. My applied force is acting up. That's some positive number. What's my opposing force? Always going to be vertically negative. So the only way that I can get a negative net force is if my negative force is bigger than my positive force, the force from the engines. That creates a negative net force, that creates a negative acceleration. So if you just want an idea of if your net force is positive or negative, look at your acceleration. If you have a negative acceleration, you have a negative net force. If you have a positive acceleration, you have a positive net force. Okay? That's the easiest way to look at this. So remember, in terms of net force, when you do these calculations, net force can go to zero if your applied force is just the same as your opposing force. But vertically, this opposing force never goes to zero vertically. This is always there. It's like you want to go out on this nice date and you've got to drag your little annoying brother who's in 6th grade who thinks he's cool and he's not. And no matter what, this is an opposing negative force to you trying to be cool. Okay? So it's always there. And in this case, the nerdiness of your brother is greater than your positive coolness, and you're going to have a negative acceleration. Okay? So it's just one way to look at it. All right. So then what you're going to do is you're going to calculate the net force. You're going to calculate the net force based upon this equation. Okay? So you're going to take the applied force, which in this case would be 7,000. I'm going to add a negative weight to it. I'm going to get my net force, then I'm going to divide it by the mass and get the acceleration. So what I'm going to try and do is verify that the calculated acceleration that I get is the same as what the computer program is reading. Okay, so you're just going to basically do this calculation by hand and then verify that the computer program is actually working like it should. Then you're going to tell me if it's speeding up or slowing down. Then you're going to pick another point. So if you come down here in this bottom left corner, there's like a slide bar here, and if you click on that, you can slide that back and forth and it will replay the trip. So if you do that, come down here, woo, okay? So what you want to do is pick a point that has a different value of the main thruster. Okay? I don't care what you pick, but just pick something other than what you want, because you want two distinct data points. So I'd write down 8,500, 0.03, negative 0.45. Okay? Then I'm going to calculate the new net force, calculate the new acceleration, see how it matches up. Now, look, at 8,500, I have a positive acceleration of 0.03. So at this point, is my applied force bigger or smaller than my gravitational pull? Bigger. By much? No, because I barely have a positive acceleration of 0.03. So when you go to land this, let me give you a little bit of a hint. When you go to land this thing, watch this acceleration relative to that velocity. Okay? Because remember, when you land, it has to land with a velocity less than -1 meter per second. So as you're approaching this deal, and you're obviously going to have a negative velocity, if you've got a negative acceleration, that means you're going to be speeding up when that thing is going down. So you can still land it, but it's going to be a little bit dodgy to pull that off. Okay? So all this is due on Moon Day. Okay? So you've got all of this to do on the back side. Pay attention to everything that I want done on this velocity time graph. The instructions are on page 3. There is a whole bunch of things that you have to do on that graph. A whole bunch of things that you have to do on that graph. So, okay,